Hi there, in this video we're going to go over an example of the Fourier transform. Now we're going to use the square wave again, and we'll show how the square wave will generate the sinc function in the frequency domain. We'll also show it in MATLAB as well, so you can get a good graphical representation. So let's say, for example, we take the square wave. Now I'll draw it actually like this, and you'll see the reason why just in a minute. If we take that there as our time axis, and that's some function of time, of course. A function of time is purely a real value. We don't have another axis here which is an imaginary axis. We have a purely real value function of time. So let's say the function of time is our square wave. So that's a square wave there. Now we know from the previous video on the complex Fourier series that we'd already derived the fact that a square wave, whenever we found the Fourier series representation, now the Fourier series representation, we'll draw that axis up there, so that there is going to be an omega axis, okay, and that's going to be all the way up there. That's going to be some function f of j omega. Now let's not get confused here. The reason why that says omega is because that's the real part of the frequency axis, okay. Now frequency also has an imaginary part there, okay. Now the imaginary part there would be j omega, okay, so that would be a j omega axis. So that would be a real part of the comp of the frequency, and that would be the imaginary part. So that this plane here that sits like that, this plane here is the complex plane, and we put f of j omega there to show that the function here is a complex function. It's a function of both the real part and an imaginary part, okay, so that's why we write those like that. Now when we did the Fourier series, complex Fourier series, we found that this followed a sinc function. It looked something like that, okay, try and get it as best I can. So it looks something like that, and it goes in that direction, okay. Now when we do the Fourier transform, what happens is that instead of the axis being an n omega axis, meaning the axis, instead of the axis being a discrete axis, the axis becomes continuous, and this function here becomes a continuous function of frequency. So it still looks the same, but it includes all the other values of frequency in between, okay. So it's a continuous function. It keeps going that direction, and it keeps going that direction. So, and again, we'll go through the little proof of that just nearer the end, but what's important is you get a comprehension of what's happening, a nice graphical kind of comprehension. So we could look at this and we can say that if we were going to do the forward transform, so we would say the forward transform would say function of time equals integral from minus infinity to infinity of, well actually the forward transform, sorry, I did this the last time I was going to this. The forward transform is going to be going from the time domain to the frequency domain. So we would say that f of j omega equals f of t times e to the minus j omega t by dt, okay. So that there would be our forward transform. Now what we're saying there, remember, is that we can approximate a function of time given a series of sines and cosines, okay. Now the sines and cosines are going to have a particular heights, okay. Now if you take all the particular heights of the sines and cosines, that will map out another function, which is a function in the frequency domain, which is f of j omega, and that's what we're seeing here. Now what we have to note here is that, and I'll go over it in the next video, okay, is that this function here is a purely real, it's a real even function of time. Now the fact that it's an even function, what we're really saying is that, I'll draw it here now, just rub it out. Because it looks like that, if we take that's time, and that's a function of time, we take that point there, then that's just some point t. That point there is f of t, so we've got f of t here. Now if we go along to the same point here, which is minus t, okay, then we find f of minus t, so we put f of minus t, then we get the exact same height, f of t is that height there, f of minus t is that height there, okay, so that there is an even function, and you can tell an even function because when you flip it over on the y-axis it's symmetrical, so it's this, all the points here will flip over to all the points here, okay, on the y-axis. So that there is an even function. I'll just rub that out just now, but I'll go through all the even and odd functions and what occurs whenever you put even and odd functions in the next video. We don't need to know all that at the moment here. So that's an even function, and it turns out that this thing here, that's e to the j omega t, well that's actually cos omega t minus j sine omega t. Now sine omega t is an odd function, so when we multiply this function here, we only get the even, the even terms, okay, because we end up with an even function here in the frequency domain. So we don't get any of these terms, and again we'll prove that and we'll show that in the next video. So all we're going to end up with is a cos omega t. So we could actually draw out that surface, cos omega t surface, because all we have is a function of two variables, w and t. So that's just exactly the same as saying, say, z is some function of x and y. So you go along x and you go up along y, and you get some function of x and y, and it maps out a surface. So the function there is z equals cos of omega and omega times t. Okay, so you could recreate that surface there in any graphical package or graphical calculator, just be putting in z is a function of x and y, such as you could write z as cos of xy. Okay, we're just using omega t here in this instance here. So let me just rub that out. Okay, get that rubber there. So we're just going to draw out that surface. Now there is our t-axis there, and again you'll see this all in full detail whenever I go and draw it in MATLAB, but for now you can just get a grasp of it here. I'll just work my way through it. So that there is a surface. Now that's your t-axis there, t-axis, that's your omega axis there, that's your omega. Okay, so now if we were to say it's going to be cos omega t, so if we let t equal 0, well there's t there, that's t equals 0 there, so t equals 0 runs along that axis, runs along the middle there. Okay, so cos of 0 is 1, so we could draw up that and it'd be a height of 1. Okay, now so that's some part of our function. Okay, now if we let our omega equal 0, that's omega there, so we let the omega there equal 0, that's 0, then it's going to run along that axis, that line there. Okay, now we're going to have cos of 0 is going to be 1, so we got a height up there, and that's a start. So that's a start on looking at our surface. Now because of, if we allow our values of omega and t now not equal 0, let them range, and what you end up with, and I'm not going to try and draw it out here, but you end up with a surface of lots of sines and lots of cosines, that as we move in this direction the frequency increases, as we move in that direction the frequency increases. So it's a symmetric surface. Okay, it's symmetric surface round about the 0 points for the frequency and time. So now if we're going to find the Fourier transform of this, if we're doing the forward transform, we're going from a frequency domain to a time domain, to a frequency domain, then we're going to take the function of time, that's a function of time, the function of time is going to modulate this. Okay, so we're going to multiply the function of time with that, Well, that there is just the surface omega t, okay, which we're drawing there. So we've now got a function of time, this here, which modulates that surface, just multiplies it, okay. So anything outside here will just be 0, anything outside there will be 0, and anything inside that value there will be a value of 1. And once we've modulated the surface, then we're going to integrate. So we integrate in with respect to time, so we're integrating in that direction. So we'll just integrate all the values up, and when we do that, you'll get this sinc function here. Now equally, if we're going to do the inverse transform, so we're going to go from a frequency domain to a time domain, then we've still got an even function, an even real function in the frequency domain, and that even real function in the frequency domain will give us an even real function in the time domain. The only difference is now, instead of modulating the surface with this function, we're modulating the surface with this function here. So we modulate with this function, and then we integrate with respect to omega. That is, we add up everything in this direction. So we add up everything in this direction here to give us this function here. Okay, so let's see it in MATLAB, because that will become a bit more apparent. So first of all, we'll look at the cos omega t surface. So let's get MATLAB up, see if I can get it. So let's see, cos omega t. Just bear with us a second while this runs up. Oh, there we go. That's good. Come up right away. Right, now, if you give us a second, I'll turn it round so we can get the frequency and time axis just the way we had it in their description. The frequency and time were slightly on that way. So that was it down a bit there. So that's just as I'd shown you. We've got a frequency along this axis. We've got our time along this axis. Okay, so up here, I can't actually draw on this, but if we had up here, we'd have our axis up here, and we would have our square wave just sitting up there. Okay, and then along that axis there would be our frequency axis, and we would have our sinc function just sitting up along there. Okay, so you can see then that if we make our time equal to 0, then the cos omega t surface will give us a value of 1, so that's just our value of 1, and the frequency equals to 0, the cos omega t will give us 1, that's a value of 1, and then as we increased our omega t, our omega, then we would increase the frequency, and if we increase the t, we would increase the frequency. So we end up with this surface here, which is a purely symmetric surface. Okay, so now what we're going to do is we'll do the inverse transform. Okay, so we'll do an example of inverse transform. What we're going to do is we're going to go from the frequency domain back to the time domain. Okay, so if I go back to our smooth draw there, and bring it up. Where is it here? Let's see, there it is for me. I'll come back here. Now, what we're going to do is we're going to go from the frequency domain here back through the surface to the time domain. So we're going to allow this function here to modulate this surface and then give us our time domain. So we're going to go from our recreate our surface. So f of t will be 1 upon 2 pi, the integral from minus infinity to infinity of f of j omega e to the j omega t by d omega. Okay, so can you see that cap that in there? So we're going to go from the frequency domain to time domain. So we have our function of j omega, which is going to modulate the surface, and then we're going to integrate with respect to omega to get back to t. So we've got our function there of frequency, which is going to modulate the surface, and then we're going to integrate in that direction there, and we're going to get this surface, this function of time here. So let's do that multiplication, the f of j omega times the surface, and you'll be able to see that again in MATLAB. So we'll pop into MATLAB again, and I'll bring MATLAB up here. Let's see, MATLAB. Okay, so get rid of that one, and I'll come up with the next one. It's going to be our surface there, sink. Okay, so it's going to be this one here. Bear with me while I just run this. It should come up. Oh, there we go. Well, that's it, come up. Now, what I'll do is I'll turn this round again so we can get our time and frequency axis just the way we had them previously. So previously, that's where our time and frequency. So we've got again our time axis running up here. Okay, so up here we would have our square wave. It come up and it would be a square wave up here. Okay, and along the axis along here we would have our sink function. Our sink function again would run like this up here, coming down. Okay, so our sink function would run like that. So you can see the sink function here has modulated the cos omega t surface. Okay, I'll maybe draw it down there, you can see it. Okay, you can see it's modulated that surface. Now, when we've multiplied f of j omega with our surface, which is our, in effect, our e to the j omega t, and we are now going to integrate in this direction. So we're integrating with respect to omega, so we're integrating along that direction, and if we integrate along that direction, the further you get out here, all of these values here will add up destructively, and the values nearer the centre here, these will add up constructively to give you your square wave. Okay, so that gives us an indication of what we're doing whenever we're going to do the inverse transform. Now the same as the case with the forward transform, you would just, the only difference is instead of this surface, this function of omega modulating the surface, the function of time will modulate the surface, and the surface will look slightly different, and you'll be integrating in this direction here. Okay, which will get you back to your sink function. Okay, so we can see then, if I go back to the smooth draw, I'll get this back up. Okay, what we would actually end up with here is an approximation to this function. So we would actually end up with something that looked like that. We come in like this, okay, and then come up like that and approximate that function there. Okay, and as you added more and more, as the distance becomes greater and greater, we would end up with something that would be even closer to the square wave. Okay, so it gives a good graphical interpretation of the Fourier transform, and it's interesting that if you treat it in the terms of purely real and even functions, you can get a good indication of what's happening. The same sort of thing we can do with odd functions as well. Okay, where we can get rid of the cos omega t and have a purely odd function, in which case cos omega t would disappear and we would only have the sin omega t, and we would be modulating a sin omega t surface. So a sin omega t surface would, let's see if I can get that up here, sin omega t, we'll get rid of this one and we'll pop up the sin omega t surface. So that should be that here. Oh, that's us. Yeah, you can see that, yeah. So if I bring that down, you can see that this is a slightly different. Okay. Okay, so again, along the centre here, previously we had 1 and 1, but now you can see the surface looks slightly different. It's a different type of surface. It's a sin omega t surface. Okay, so again, if we were approximating functions, so we were transforming functions from the time to frequency domain, we would just be modulating the surface and then integrating in this direction. Okay, and in the same way we'd be modulating the surface if we were going from the frequency back to time. We're modulating the surface with the frequency values and then integrating back along that direction. Okay, so that's enough. It gives you a good indication there of what's happening there with the Fourier transform, but also remember that these are just graphical representations. If it helps, then that's good, you know, and there's a lot of the stuff in the transform, the Fourier transform, Laplace and Z transforms, that you can get a grasp of them. A lot of the properties from a graphical representation. But I think it's best and it's good to also have a comprehension of these things in terms of linear algebra and vector spaces. So let's just finish off and we can do the little bit of maths that shows that the Fourier transform. Okay, so let's go back into our smooth draw here. I'll bring it up. So if we were going to go and do this, we would let's say we're going to do the forward transform. So we're trying to approximate, or we're taking the function of time and we're trying to find the frequency components. Now I'll probably stop using the word approximate, okay, because we know this is based on the idea of one function approximating another function, okay. So we're transforming a function f of t and we're finding the frequency components of that function e to the j omega t respect to dt. Now if the function's a square wave, then we can say that f of j omega equals, and now if we're doing the square wave between, if that there is tau, we're doing it from tau by 2 to minus tau by 2, so we could do then integrate from minus tau by 2 to tau by 2, and now f of t is just going to be a height of 1, okay, so it's going to just be 1 times e to the minus j omega t by dt. So again, that's just going to equal, when you integrate that, it's just going to be that will remain e to the minus j omega t, and it would be over j omega, okay, and the minus sign would come out there, so it would be minus that, okay, and we'll be integrating that from top and 2 to minus top and 2, and if you work through that there, it's going to give you e to the j omega tau by 2 minus e to the minus j omega tau by 2. Again, I've went through this derivation whenever we did the Fourier series, the complex version, so the derivation is just almost the same, okay. There's j omega, and okay, so yeah, then what we do is, the little trick we do is we're going to try and get this in terms of the sinc function, so to multiply by top and 2 and divide by top and 2, okay, and that there then gives you your value f of j omega equals tau, and it's sine omega, sine a half omega tau all upon a half omega tau. And remember, when we did the Fourier, the complex version of Fourier series, it was top and t naught, but the t naught has now come up, okay, and it's part of the derivation of the Fourier transform, okay, which was in the previous video. So all we've got there then is the frequency domain omega, and it would look like, it looks like that there, okay, and the height there is tau, and these are cut overs at 2 pi upon tau, okay. So that there is just the derivation, the mathematical derivation. Now what I'll do is, next video I'll go over the even and odd functions, and I'll show you how we can look at those surfaces, the sine omega t and the cos omega t surface as separate surfaces, and we can see what happens when we find the Fourier transform of real even functions. Real odd functions are real functions which also have both even and odd terms in them. Okay, but we don't find the Fourier transforms of complex functions of time. Okay. Okay, so that's all there is to this video, and I'll get you in the next video. Okay, bye bye.